Everybody. Welcome from Ottawa, Ontario, the capital of Canada. And I know that you have had so far very extensive learning experience. And so and also I heard that you're going to have another session after dinner tonight. So with this, I'm going to try to be as brief and as pointed as possible in my presentation. I'm going to walk you through or introduce you to the world of Tidymodels. It's a new coding system that deals with machine learning problems within the environment of R. It was originally developed by Max Kuhn and then other people at RStudio. So the presentation will walk you through several steps in completing a machine learning example. The example will proceed from the starting preprocessing data stage onto the model construction, and then on and finishing with an assessment of the model and how it performs when you fit it with unseen or when you test it with unseen data. Now, why Tidymodels? Well, fundamentally, Tidymodels is an ecosystem package which was specifically designed with a common API and a shared philosophy. Most of us have extensive experience with R, but we know that there is a consistency problem with R. Many people have developed many different packages using many different principles, and that means we have slightly different interfaces to do the same kind of thing. So with this problem, Max Kuhn decided to develop the idea of Tidymodels. You may have come across the name Max Kuhn before, since he developed an additional and early package called carrots. And so now we have, and he has said, at least he's told me, that the carrot package will be maintained, but it will not be updated anymore. So this is why that Tidymodels has come on the scene. This particular slide has a lot of ink in it, so I'm just going to jump to the last sentence here and mention then Tidymodels works through a series of steps of basic machine learning modeling and implements a conceptual structure that makes complex iterative workflow possible and reproducible. Well, that's really a mouthful. And so that if you really have time, sit down and parse this sentences, and it becomes really then a really statement that has a lot of meaning to it when you think about it. So who am I? Well, my name is John Lewis. I was a professor of climatology at McGill University for 28 years. After I retired, I did a degree in statistics, and for a while then taught short courses in spatial statistics. In the last few years, then I have been concerned with working with machine learning. These are my two contact points that you might be interested in, the GitHub, and this is where you can find the information on the slides and material that I'm presenting today. And also in there's another repository that goes a little bit step farther and dives a little bit deeper into Tidymodels workflow. This has bothered me for a long time in terms of where we fit within the kind of conceptual area of artificial intelligence. I might add that there's a lot of discussion that intelligence is never artificial. But anyway, that it's in this second kind of circle that you see here that my main work has been done in machine learning. I've done a little bit in neural nets when we get a little bit more complicated in terms of the model formation, but it's within this particular outer circle here that you see as machine learning, which I consider the kind of classic approach to this particular problem. And what I mean the classical machine learning, what we're talking about here is looking at supervised and unsupervised techniques to solve a particular problem. For this presentation, I'm going to concentrate solely with the left-hand side of the diagram, and that is concentrate on supervised classical machine learning, and primarily with the direction of regression in regards to a problem that I'll present during the presentation. But we can also look at classification, where we're predicting categories, or in terms of what we will do today is predict a number for a particular output. This is something too that bothers me about the question of machine learning. The person on the right says, or person on the left says, is this a machine learning system? And the fellow standing on top of that pile of whatever it might be says, yep, you pour in the data into this big pile of linear algebra and collect the answers on the other side. And then the fellow on the left says, what if the answers are wrong? Well, the guy says, just stir the pile and they start looking right. Well, this is a serious question about what you do. It's kind of like p-hacking, that we just keep on doing and doing things until we get something that looks right, and we say, well, that's a nice model. There's another problem that bothers me too with machine learning. And a wise man once said, the wise man wasn't me, by the way, just because you have a bag of hammers does not make every problem a nail. So in this sense, we have a lot of sophisticated tools within machine learning, but it's really not the driving force. The problem becomes the driving force, and we look at a particular tool to solve that problem. So now what are the goals of this presentation? That the first thing is to explain key concepts of Tidymodels. The second thing, we'll use Tidymodels and its companion packages to produce output for a machine learning regression model. Thirdly, I'll illustrate our code on how to program the workflow sequence for machine learning models. And this is the thing that I want to emphasize during this particular talk, is that you will see how really simple it is to start and complete a workflow problem with TidyFlow presentation or TidyFlow coding. Now, the two assumptions these are not substantial assumptions, but still, that you have to have a working knowledge of our language. Well, I believe with the group that's I'm talking to, this is not a question of concern. But you should also be familiar with some machine learning material. I'm not going to go into a lot of detail and explanation about certain particular processes within the machine learning environment. I'm just going to assume that you know a little bit about that, and that we will emphasize the Tidymodel coding of that information. So this is a diagram that most of you probably have seen many, many times. It's the famous Hadley-Wickham diagram of the tidyverse ecosystem. And so I just wanted to present this at this time to show you how the Tidymodels environment or ecosystem fits in with this overall idea of the tidyverse. So in the left-hand side, we see here, upper part, the importing of the data, constructing a tibble with the particular packages that are involved with importing data. Then the dplyr package, where we can use data wrangling techniques to transform the data. Moving on around the circle to visualize or do some exploratory data analysis with ggplot2. And then finally coming around to the circle, which encompasses the whole area of Tidymodels, and that is modeling your data within this particular kind of tidyverse universe. So now I'm going to get into the Tidymodel program flow. And in this, I'll show 5 steps and the packages that are associated with Tidymodels. The first, Tidymodels itself, is a meta package. It really is an umbrella for a whole series of packages that are associated with this particular ecosystem. So the first step that we do, and you can think of these steps also as procedures or methodology in regards to coming from the start to the finish of a machine learning problem. So the first package to introduce is the recipe package. And this is an interface for data pre-processing or feature engineering. This sentence also brings out a particular problem that we have with terminology, and that you just have to get used to different words meaning the same thing depending upon the discipline that is using or that has written the particular literature that you're reading. For instance, data processing, or pre-processing is used in statistical literature, where the computer science people tend to use feature engineering. So this is a pre-processing step, as we'll see in regards to setting up our data for later use. The second package of importance here is RSample, and this provides an infrastructure for efficient data splitting and resampling or cross-validation. You know, see, RSample is one program that kinds of moves around in these steps, because we'll use it first to produce a holdout sample, and then secondly, we'll use it for cross-validation of the model itself. The third step then becomes really the heart of this particular workflow, and that's the parsnip package. It's a package that contains interface to some odd 30 models within the R environment. And so you have a range of these models where you won't get down, you won't bog down in the kind of minutia of the format of these underlying packages. Once we have the model, many of these packages have hyperparameters, or parameters that are not then being able to handle by the learning algorithm itself. And so we have to tune the model, and there is a package, obviously Tune, that does some of this particular work for us. And finally, after we have a tuned model, a fitted model that is optimized the particular hyperparameters, we need a package that will measure the effectiveness of the model, and this package has a series of performance metrics that can be used to do that particular operation. There are other important packages here that I'll mention. The one on the left, the workflow, is a relatively new package, only about 4 or 5 months old. And what that does is kind of bundle pre-processing, your modeling information, and your post-processing data together. And so it's kind of like a placeholder where you don't have to continually carrying through these specific kinds of objects through your workflow. The second one in the middle is a kind of adjunct to the tune package. This is referred to as dials, and this manages some of your tuning packages and also lets you use more sophisticated search techniques in regards to developing a parameter grid structure. The one on the right then is really a second cousin, an adopted second cousin of Tidymodels, because this package has been around for, at least 3 or 4 years. And this is the Broom package. And what that helps you do is to convert a statistical output for model objects into some type of user-friendly format. So if you want to learn about the complete environment of Tidymodels, then you can go to either one of these two particular websites. There is a substantial amount of data that you can access from RStudio and their Tidymodels site on the web. We'll look at some of this stuff later on. Okay, now we're into the actual kind of program description. The first thing we want to do, as always, is to load our models. And in this particular example, I'm only going to load 2 libraries. One, the tidyverse, and the second one, the library Tidymodels. If you do not have this, obviously, you just have to install it from CRAN, and the install package function can be used to do that. When I said these packages are, or the Tidymodels package, like the tidyverse, is an umbrella type of package, this is what I mean. If you're familiar with tidyverse, you can see the kinds of programs that are here, ggplot, the dplyr program, and so forth. But I just want to draw your attention to the lower part of here of the packages that are within the Tidymodel environment. You can see here there are 10 different packages that are loaded at the time when you execute library Tidymodels. 7 of these, or 8 of these packages we have already seen: broom, recipe, RSample, workflow, yardstick. There are 2 that you don't see here, and that is model data, where this is a package that has a lot of example data sets in it that we can use for examples, for problems that we want to show in instruction and so forth. And the last one, infer, lets you do certain kinds of inferential types of operations, which I really have not used and I can't speak to with any in any way. So those were the packages that we have to use within the tidyverse, Tidymodels environment. In this particular example, we'll be using the Ames housing data set, which contains 81 variables and almost 3,000 observations. And you can see with the statement below here that I just load the Ames data from the package that we have loaded, model data. The dependent variable that we're going to use, and this is another particular example of complex terminology or overlapping terminology, and this could be called the dependent variable, the response variable, the target variable, the outcome variable, but in our particular case, the name of it will be the sale price of the particular housing in this data set. So in an actual analysis, we would spend much more time exploring the data set, but for the sole purpose of demonstrating the Tidymodels workflow, we'll just perform a variety of preprocessing, throw a relatively simple model at the data, use some cross-validation techniques in tuning the model, and then take the fitted model and test it with some unseen data. So you'll see that I have, just with this gray background, these are the statements that I would have in my R code to do these kinds of operations. Most of us have a substantial geographic background, and so we want to see a map, and this is the area where the observations were collected. It's Ames, Iowa. It's just north of Des Moines, Iowa, in the heart of the Midwest United States. Ames, Iowa is a university town. It's where Iowa State is located, and as a side note, it's the university where Hadley Wickham obtained his PhD. But for us, we can see that there's color-coded here about 16 different neighborhoods that are involved in the collection for the observations that we have. It gives some indication of the spatial distribution of the information. So just to check in terms of whether that I really have 81 variables here, the columns that I specify and the rows that I specify for the observations, you can see are 2,930 different observations. With column names function, I can get a list of the columns, and you can see here I only listed 65 that fits on to the actual slide itself. There's just a bevy of different variables that I can use here as predictor variables, but in this particular case, well, this is another example of the showing of the information on the different variables in the data set. In this case, I use glimpse, and the reason why I like to use glimpse sometime is it gives me information about the data types. So you can see here that many of the data are factor type data or nominal categorical data, but I do have some decimal, integer, and things of that sort. So we have to pay particular attention to that in the pre-processing because models take different kinds of data input. Some models can work right away with nominal or categorical information, and other models you have to then do some type of dummy coding. So we can take a look at some of the data points or the data predictor variables that we have with these data plots. And the first one I just picked out is the living area. This is in square feet, thousands of square feet. And so you can see the kind of distribution. So we have to look at these kinds of things before we engage into the actual model development. We have to look and do some exploratory data analysis on this information in the data set. On the bottom part of this slide, you can see I did quickly just a simple kind of linear model association with this variable and sale price. And you can see the kind of fits here with the subset of different housing types, whether it's a duplex or a single family home or like that. However, for this example, I have chosen only to use two variables. And this is just for simplification and not present an overly complex kind of pre-processing data step. So I'm going to use longitude and latitude. And in some cases, this is nothing more than a surrogate for some of these other variables that you see listed previously. This is a slide of the response or the target variable. This is sale price, and this is the variable that we want to predict out of our regression effort. The top slide shows the count, and you can see that it's a skewed distribution with a long tail to the right, and this might, for some particular models, cause some bit of a problem. The lower one, then, I've done a log transform on, and so we have then a more normal type distribution shape in the form of this log normal graph or histogram that you see here. So these are the focus variables that I have. 2,930 variables of sale price, longitude, and latitude, and I just display here the first 5 that we have. So the question is, what are we going to do with the data? Many times that I've seen that we focus almost primarily on the model construction or the center part of this diagram over here in this particular space here. That occupies a large percentage of our effort. But this is not the important part in terms of machine learning as far as I'm concerned. That the pre-processing and the post-processing of this data really has a substantial impact on the outcome. One of the things you can see here, if we don't pay particular attention to the pre-processing of the data and the post-processing, is that we might actually end up overfitting the data, and really the model has no generalization properties at that particular point. So now let's start the actual modeling workflow. We've loaded our data on it. We have the particular packages that we want to use. And so the first thing we want to do is create a holdout sample. And in that case, we split the data into a training set and a test set. And in this particular case, that's why I say that we kind of flip around in using the RSample package, that we will use that to do this holdout sample. So in this particular case, you can see that I have my original data set here that I split it into, in this particular case, called the old data or the training set, and then save some of it or partition some of it into the new data or the test data. Now, we don't want any kind of leakage, data leakage from the old data set into the new data set when we're running our program through to the endpoint. So these are the code descriptions that we need to do in doing this data partitioning. So we set a seed because we randomly then split the data in some way. Remember, Ames is our data set, and this is the initial function that we use to do the split and create an object called Ames split. You see over here, there is a variable of prop, which is the proportion that we want to make into training versus testing data. And so if I print out the object Ames split, you can see what has happened here is I have 2,051 data points in my training set, and this is the data set that we set aside as our testing set, giving us the total with the addition of the 2 of the starting point. So creating then the training set, I use the training function on the Ames split data set or data object, and I create my Ames training data set. At this time, I usually then also set up the cross-validation exercise, and that is the statement right here. I use a v-fold cross-validation, and I do that on the Ames training set and create a new object called Ames CV or cross-validation. We'll talk more about this in just a few minutes when we actually do the cross-validation. So the next step is define a recipe. In this particular case, then we really are doing the pre-processing steps. And the recipe, in the formulation of the recipe, we subdivide it into a formula and into particular steps that either do transforms, normalization, take care of missing data, dimension reduction, or a whole bevy of kind of things that are available to you. So you can see, as I said, that the recipe is in 2 parts. We first specify the formula, just like we would do in a regression equation where we specify the response variable, and then on the other side of the expression, we specify the particular predictor variables that we're going to use. In the second part of a recipe, which I'll show you in just a minute as an actual one, that we specify the pre-processing steps. In this case, it may be dealing with missing data. It may be creating dummy variables for categorical information. It may be scaling or normalizing it. It may actually be just removing a particular variable that we don't want to have in the process, in the machine learning process. So this is a pre-processing statement that we're going to use in our particular recipe, that we have the function recipe that is here, and this is the formula that I'm using in terms of my regression expression. The sales price is the response variable, and longitude and latitude are the 2 predictor variables which I'm going to operate on with the training data. This is the second part of a recipe, and these are the steps or pre-processing kinds of information that I use to change the character of my data. Well, in this case, I simply use a log transform on the sale price in converting that to log normal. We could have used many more variables. We could use the whole set if we wanted to, if we had time to go through all of the kind of pre-processing that may be needed to do this. You can see here, again, I have the same structure to my recipe, that I have the recipe and the formula, but in this case, that I have used the dot object or the dot variable here that includes all the variables of my training data. And to do that, then I have to set up a whole series of important pre-processing steps. First one is the same that we used before. You also notice I'm using the pipe operator here, that if you're not familiar with this, you can think of this, and then we do this, and then we do this particular step. And so the second step is the Joule-Johnson transform. It's like a box Cox transform, but it can deal with values below 0 or negative values here. And so I look at greater living area and lot area and do a transformation on that. I do a pre-processing on the neighborhoods where I set a threshold that anything under 10% in terms of frequency goes into a bin called other. I do the dummy variable conversion on all the nominal data. Some of the predictors may have 0 variance, and so I exclude those. And I could even then tune my predictor variables here in setting a spline to the longitude and latitude, or whatever particular predictor variable that you want to tune before the particular next step goes into effect. So these are some of the reasons quickly to modify for modifying your data, because some models in this particular package of parsnips requires that the predictor variable have the same units. So you need to center and scale the predictors for this particular purpose. Other models are sensitive to correlation. So if you have multiple linearity with the predictors, then you need to either filter or do some kind of signal extraction with PCA to improve the model. Scaling the predictors, I found, using certain kinds of transformation can lead to big improvements in the model output. And many models cannot cope with missing data, so you have to spend some time with imputation strategies in regards to the particular model. In some cases, the data could be encoded in ways that might maximize the effect of the model. So in this particular example, the date for the day of the week can be very effective for modeling air pollution. So you could specify a particular day of the week in your pre-processing recipe. So now we have gone through the holdout sample. We've done our pre-processing, and now the next step is the real functional area of the Tidymodels, and that's the modeling construction. And we use the package Parsnip, which offers a unified interface for a little over-exaggerated statement. I say massive variety of models, but a wide variety of models that exist within R. So this means you can have only one way of, this means that you only have to learn one way then of specifying the model. You can use a specification to generate a linear model, a random forest model, a support vector model with only just a few lines of code. So how do you specify a model under Parsnips? Well, there are 4 things that you must do in terms of specification of the individual model. The first, obviously, is the model type. In this particular case, if we're going to use a random forest, or we're going to use a logistic regression or a lasso model, whatever it is, we have to specify the name of that particular model type. The second thing is that there are many underlying packages that come or that exist in R that do the same type of thing. For instance, with random forest, I think there are 2 different packages. Well, in this case, we would use set engine and specify Ranger as the engine that I want to use to run the random forest program. The mode is just a simple binary between classification and regression. Some packages can do both, and so we have to tell then the workflow whether we're going to run this package as a classification exercise or as a regression exercise. So we do that with set mode. And finally, the set argument function then enables us to put in information about how we want to tune or what hyperparameters we want to tune in our model. This is just a short list of all of the particular models that are accessible via Parsnip. The first line here, the first common models, I consider common models, that you can do both classification and regression with. All these BOAST trees, XG BOAST and things like that, decision trees that you can run, multivariate adaptive regression splines, neural networks, nearest neighbor, random forest, different varieties of support vector models. If we go to just classification models, then we find logistic regression and multinomial regression, and just for regression, linear regression and survival regression. So I can go here to the URL for parsnips, and you can see all of the different particular models that you have. You can explore the models here, and you see that there are over 30 different entries here that you can use in terms of choosing a particular model for your use. And then below that, you can explore the model arguments. If you don't know them a priori, you can see that I can look at the model type, the engine that I need, the other kinds of information that are listed here. So there is help that you can come to if you are not familiar with the particular characteristics of a model type. Okay, so now I have to go back to my full screen here. Okay, oops, that's not what I wanted. Sorry, let me do that again. Okay, and I'll go back to full screen this way. So that's where I ended off by showing you the kind of protracted list of models within the parsnip environment.
John, we have
So
a
now
question.
where are we? Well, we have split.
A question. If you open the Q&A balloon on your Zoom, there's one person ask a question about the.
I can't see that on my screen. Okay, up here.
Yeah.
All right.
You see the question? So the question
Right.
is, if they're missing data, NAs in the training or test data set, will
No, our sample, what you have to do is take care of that in the pre-processing, depending upon the model characteristics. Like if I'm familiar with random forest, you don't need to worry about missing data.
Okay, but the good idea is that we do the removal of, so we just do complete cases or something.
Well, what you do, yes, you can do in terms of dealing with missing data, you can impute, you use nearest neighbor, you can use median values or whatever that you want to use to impute the data that's missing. Or you can just delete it if you have 5,000 observations, if there's only a few there that are missing, right?
Okay, yeah, please continue.
Okay. Okay, so as I said, that we have split the data, and you see here that I have kind of grayed out the new data because we don't want any data leakage from our training exercise into this particular test data or unseen data. So now we're at the point here in the succession that we're going to train our model. So with the parsnips, I can quickly just fit a model if I want to, in this case, without doing any tuning of the model itself. And so you can see here that I've specified the nearest neighbor as the model type. The mode is regression. The argument is 5, and I set the engine as this particular package within R. So then I create a fit statement here that I go down and actually fit the model here that I specified in terms of the formula we used, sale price, longitude, latitude on the Ames data. And so that I quickly then get some kind of output then for a non-tuned model. But really, we don't want to do that. We want to really then have the facility of looking at and trying to optimize these hyperparameters that are involved with these different packages, these different models. So let me say a few words about nearest neighbor models if you're not familiar with them. First of all, it's a relatively simple supervised algorithm where each observation is predicted based on the similarity to its nearest neighbor, as you would suspect. So these algorithms, or this type of algorithm, is easy to understand and enables better interpretation of your results. This is one of the things that I like to do, as I like to start off with a simple model and then eventually go to more complex models in regards to the process. Nearest neighbor makes no assumptions about the data, such as its distributional form, when it can be a valuable kind of assumption. It may not provide the best prediction accuracy, but it works well with a variety of different data sets. And as I mentioned just previously, it can be useful as a pre-processing purpose in terms of data imputation. So now we really want to define the model specification, where we look for tuning values, that are parameters that we want to specify and not just consider as default. So I specify the nearest neighbor, and then I set my arguments here, the neighbors, to tune, and we're going to tune two different hyperparameters for the nearest neighbor model. We're going to tune the number of neighbors that we use, and we're going to tune the distance power in terms of the exponent that we use. Then we set the engine to something we saw before, and we set the mode to regression. I am going to diverge a little bit here and introduce this package of workflow. As I said, this package can handle or can bundle together pre-processing modeling and information and post-processing requests. And so we don't have to fiddle with the individual kinds of details that come with keeping the recipes and keeping the tuning and all that kind of stuff together. And so this is the statement to create a workflow object. I use the workflow function here, and you can see I add the recipes or recipe here in this particular statement, and I add the model and the model specification statement, and I create a new object of ML workflow. Now we're at the stage of tuning the hyperparameters. We have chosen two parameters to tune. If you have no hyperparameters, you can skip this particular step, or if you want to, you can let the machine do some of this particular work by just telling it these are the parameters that you want in terms of giving these parameters beforehand. But in this example, we'll do the tuning using a v-fold cross-validation. In this case, I'll use 10 v-fold objects, and we have previously created the cross-validation object. And so now I want to specify the range of the neighbors that I'm going to test the parameter space over, and same thing for the distance squared object. And I'll use the previous workflow with the function tuneGrid to do this. This is an example of a diagrammatic version of a v-fold cross-validation. You can see here the data is randomly subdivided, in this particular case, with 10 different segments or folds. And so that I create a fold then of assessment, of analysis data and of assessment data. So in the first particular fold, I run the model on one, excluding the assessment data, and I test the results in terms of performance matrix with the assessment data. And you can see here in this that I've repeated this, or I repeat this 5 different times. So I just don't have 10 runs of the model. I have 50 runs of the model in terms of testing it and its performance. In this particular case, what we'll do is add or average the values of these 5 and get 10 values then of the performance matrix for the 10-fold cross-validation. You can see the steps that we take here. At first, we create the holdout sample. This is our testing set here. Now we're into the cross-validation of the training set in terms of attempting to optimize our hyperparameters. So we create sample 1, and in that sample we have the analysis that we then look at or test it against the assessment data. So you can see the problem with the naming of these particular things. This may be called validation data, and there's lots of confusion, so you have to pay particular careful in terms of what this particular word means in terms of the literature that you're reading. So in this case, then we have sample 1, sample 2, on out for our example of 10 folds, where we then take the analysis data and test it with the assessment data by fitting the model over and over again. So this is the statement that I can use to tune the model. And now I introduce the tune package, and also to give some kind of performance metrics, I introduce the yardstick package. And so I have the workflow information here that gives the routine the information on the recipe, and it gives the information on the model specifications. And then I use the function within tune grid to resample or do my cross validation here, and I specify a grid of 10 values each for the number of neighbors and for the distance exponent, and I test that in terms of the root mean squared error and my performance metrics. Now you can use other kinds of things besides just a simple listing of 10 values for your hyperparameter and search space. In this particular case, I can use on the upper diagram, I use a regular grid here of 5 by 10 observations here of the plot of one of the hyperparameter variables on the y-axis and another hyperparameter variable on the x-axis. Or I can use a non-regular grid for my search, and that is picking out random points within the particular parameter space to do the same kind of thing of trying to find the optimum value for my hyperparameters, with one particular value of the hyperparameter on the y-axis and another on the x-axis. So where are we here now in terms of this overall operation? Well, we've done the resample here of producing the holdout sample. We've used recipe to pre-process data and supply a formula that we're going to use in the regression. We have specified our model in terms of the nearest neighbor, and we've tuned that model and validated the model, the trained model, with our performance metric. Let me just say a few words about yardstick, and I'm not going to really go into detail with all the different kind of metrics that are available to you. The first two metrics here are for classification types of problems, such as accuracy, sensitivity, and the receiver operating curve, or the ROC curve. The one that we really are interested in for the problem at hand is the regression metrics. And in this case, we can look at root mean squared error, R squared, mean absolute error, and for our problem, we'll just take the first two here and look at it. Again, you can go and look at a URL to look at all of the different choices that you have for the metrics that are available. And this is a simple expression then, where I've taken the output from my tuning here, in this case, and then just supplied a yardstick function called collect the metrics and piped it into or made it into an object called res, or the results. And so now I have the print results of my exercise of the 10-folds of the different values for the neighbor of hyperparameter was tested, the distance power value that was tested on my metric root mean square, and this is the mean then of these particular values, and out of that then I would pick the optimum one that would produce the minimum root mean squared error. Or you can see this a little bit better with this plot, where I have on the left-hand side the distance power, and you come and you want to minimize the root mean squared error, and so this particular value looks like the one that would minimize that and pick that for the optimum. And over here, the number of neighbors that we have, we pick that for that particular hyperparameter. So we're almost home now, because we have a fitted model that has optimized and been tuned. And in this particular case, now we want to update our workflow. And in this particular case, we want to then select the best value, the best parameter from the tuned object. And so we do that here by, first of all, using the tuned object here, and we use the function select best, whatever metric it is that you want here. It's the root mean squared error, and I create a object called best parameter. And now setting up the final workflow here, I have my workflow from before. I use the finalize workflow function to input into that workflow the value for the best parameters of my hyperparameters and create a new object here called aimsRegRes. So again, just to give you an idea where we are, now we're starting to look at the new data, because we have a trained model data, and now we want to do the predictions on the test data to see how well this trained model operates. The thing here I just want to focus on is we'll use a function called last fit, because now we have all the information we know or we need in the workflow object. And so now all we have to do is supply the last fit function, and we then look at the test data in that way. So I have the output from the previous a particular operation. I apply last fit to now look, I'm doing that to the split data, because the split data has both the trained data and the test data in it. And so I come out with an object of my fitted information. And so now, just to complete this, I've done the predictions, and now I want to look at a performance assessment of how well the trained model then dealt with this unseen data, or the test data itself. And so this is the test performance then, and I use a function similar to what I showed you before of the collect metrics, but in this particular case, then I'm collecting the metrics on the test data. And so I have the fit function here of the final model. I collect the metrics and I print out the metrics, and you can see I have then the root mean squared error for this particular ability to predict from the unseen data, and the R² value of this very simple regression that we have with two predictor variables of longitude and latitude of 0.7. And we can actually do this on the prediction set itself, then again using the fit object here, creating test prediction from collecting all the predictions together and printing that out, and you can see the predicted value in log space, okay, and the actual price in log space here of the observed data. And we end up with a plot then. This is, granted, this is log information of the sales price of the observed data versus the predicted data. Now, the results of the model performance, in my estimation, are not great. But remember that we've only used 2 predictor values, and these really, longitude and latitude, are surrogate information for a lot of the other predictors that you saw at the outset. But in some ways, that, as I say here, the real job of modeling house sale prices starts now. And I will talk a little bit about that in just a moment. How's our time, Tom? We got a few more minutes?
Yes, we have
Okay.
time, but please leave some time for the questions.
Okay, well, let me just go through this quickly then. And so we start out here, and there's in the square box, you can see the package that I use to start with the recipes. We then go to use specifying the model. We tune the model with the help of our sample and the cross-validation. We fit the model, and we do some kinds of assessment of the fitted model through cross-validation. And then we come out with the optimized model, where we test with it on unseen data and perform some type of metrics with that. And that completes the model flow from the beginning to the end, which I said it was the object of this particular presentation. I'll skip this. You can do this on your own, but if you do a kind of elementary kind of matching here, and if you get them all right, then I'll consider you as an expert on Tidymodels. I have added additional information to the particular presentation that if you go to OpenGeoHub slides 2, you will find a more sophisticated nearest neighbor model with many more predictors used in it, with many more kinds of pre-processing steps that I've used. And also, along with that, I build a random forest model and a lasso model, and I compare the results of these particular 3 models. And in addition, I do more explanation of cross-validation techniques and the bias variance trade-off and the problem of overfitting. And finally, you will find in our markdown file there that I've done a classification exercise on a previous Tidy Tuesday data set on the global volcano data, and you can see how a Tidymodels, a tidy exercise on classification. Okay, these are some references you can look at later that I have used. These are further resources in terms of material. Some of these I've already dealt with. The last one you can see is the material within the OpenGeo slide 2. And that I will end with this. If you're familiar with the very classic movie called Alien, probably most of you weren't born before or at this particular time, but anyway, that it's been on TV for many, many kinds of viewings. But in Alien, there's a famous quote, and it says, "In space, no one can hear you scream." So hopefully that after this presentations, and luckily with Tidymodels, it'll provide a much friendlier place for you. I think that in my estimation, there's an ease of adoption, there's an ease of use of the fundamental design characteristics within the Tidymodel ecosystem. So that's the end.
Okay,
thank you.
Thank you.
I just wanted to say thanks to Max Kuhn, Allison Hill, and Julia Silgi for all the insightful material concerning Tidymodels that they've made available on the internet. This really has made my presentation possible. Thank you again.
Thank you so much. And let's have some questions. I will. Somebody might ask in the audience, and then I will repeat it. So, who wants to start?
So the thing here, Tom, is really to go back. I supply the R code in terms of one particular file that they can use to execute this from start to finish. And they'll see that with just a few regularly lines of code that you can come out with this kind of output and have all these different options at your fingertips.
Okay, and my question is, you know, I'm a more, I use more MLR.
Okay, I failed to mention, I wanted to do that. There are other packages within R that you can use. MLR is old now, as you know, and it's MLR3 that they're rewriting it, and that's another excellent package that I've used periodically. There is also H2O, which is much more sophisticated, and it actually has AutoML attached to it and things of that sort. So all I'm showing you here is a simple introduction into machine learning where you quickly can get in and get some kinds of answers.
Okay, and when you use the Tidymodels, is it are they automatically parallelized, or how is it difficult to compute with a bit larger data sets?
It's fine with them. I mean, it's just granted the different models have different kind of computational requirements. That you can do a nearest neighbor model with 10,000 points, but if you the computational time increases linearly with that. So it's not the tiny models itself, but it's the model itself, the particular machine learning model, whether it be XGBoost or random forest and like that, in regards to its computational demands.
Okay.
The thing is that you can parallelize it though. Random forest, XGBoost, and things like that can be parallelized within Tidymodels.
Oh, by the way, I think that one question popped up from the people on the Zoom. How you do ensemble modeling in Tidymodels? Is there support for ensemble models?
Okay. Thank you.
Thank you so much. And yeah, that's very useful.